Welcome back again to the Marine Hydrodynamics course. So, just to jog up your memory, we ended the last lecture with the material derivative concept. So, the material derivative concept was nothing but just enter any Lagrangian equation here, and the material derivative of that particular function will give you the rate of change of that function as you flow along a path line sitting on that fluid particle. So this basically means is that suppose you have a path line with many particles, and suppose you choose this particle. This is a lucky particle in which you are sitting right now, and then uh, if you want to find out the rate of change of, let's say, its velocity, or let's say its pressure or density, right? So you take its material derivative to find out its rate of change of things. So that is the material derivative. So before moving ahead, let's also talk about two other terminologies, or two other concepts, in fact. So, which is the concept of steady flow. So, what do I mean by steady flow? And this will play a really important role when we are trying to derive continuity equations, conservation of mass equations, etc. So, let's say I have a river. There are this. Let's say this is the sea, and this is the water is flowing inland, right? So if I actually draw my sensor, so if you remember, we had used a sensor like this to measure the velocity at this particular point in space and time. Actually, I had done that in orange, but let's say I chose the sensor color to be uh, purple or pinkish. So what I do is I measure the velocities of these particles at time, and I should get a constant velocity at this some particular space and time. So if I'm getting a constant velocity, that is del by del t equals to 0, right? Del by del t equals to 0 means that it's a steady flow. That is, the particles are not accelerating here or something. Note that, of course, the fluid velocity could be different at this point, right? The fluid velocity could be different at this point, could be different at another point, but in particular, it's not, the fluid velocity is not changing at this particular instant. So if I sit here, I'll see all the particles going by a particular speed, whatever that velocity would be. So just to note here is that the partial derivative of time is 0 here, but the material derivative capital d by dt is not 0, because if we are talking about the material derivative, we are sitting on the particle and then analyzing its velocity. Of course, the particle will move through different regions in space and times, and therefore its velocity will also keep on changing, and therefore capital D by dt is not 0. The del t, which is at this particular space and moment in space and time, the velocity is constant, or is not changing. So that's the concept of steady flow. Then we have another concept, which is a concept, again an important concept, and actually a very good practical approximation, which is the concept of an incompressible flow. This is the concept of incompressible flow, and what we mean by this is that the density of fluid particle, or the density of a water body, does not change with time. So that is what we are assuming, because density is at the end mass by volume. If the mass is remaining change, if the volume decreases, then the density would increase. If the volume increases, then the density would decrease. But since it's an incompressible flow, I cannot compress water, nor can I decompress, something like that. I cannot compress water, and therefore the change in density must be 0, right? So this is actually a Lagrangian concept, that is capital D rho by capital dt equals to 0. So this is that is the material derivative of density should be 0, which means that if we take this particle's density should remain same throughout, right? But this is not the case. But do not confuse this with that del rho by del t should be 0. It's not necessary that del rho by del t should be 0, because del by del t, if we come to these small del notations, we are considering an area, and under this area, suppose the volume changes, then the density could keep on changing at different points in time depending upon the specific volume at that area and other factors. But the material derivative, which means that the density of water won't be changing, right? So that's the important aspect. So these were really two simple concepts. Now we move on to our first equation, which will use the first tool of physics, which is conservation of mass. So what we're going to do now is, let's say you have a material volume. Now what I mean by a material volume is that I have fixed volume, and let's say this is water, and I'm going to call this Vm, and let's say this material volume is a function of time. So after a certain period of time, let's say this volume moves somewhere else, or this volume increases, decreases, and so on. So I have this material volume, and for now I'm going to assume it fixed. And the mass of this material volume, so this is, let's say this is the mass function, which takes in the material volume and then spits out the whatever the mass you get, is the triple integral, is the volume integral. So that's why I've written triple integrals here, rho dV. So as we know that density is equal to mass by volume, and therefore mass equals to density into volume. So that is what I've done here, rho dV, and then I've triple integrated through the whole volume to get the whole mass of this particular control volume. Now what does mass conservation say is that if I have a control, if I have a material volume, the mass inside the material volume should not change, right? Because I'm not adding something from here, nor am I taking out something from here. Therefore d by dt mvm is equal to d by dt both sides, and the, d by dt is nothing but the change of this mass with time, and this should be equal to 0, right? And therefore I will have 0 equals to d by dt triple integral rho dv, and that's actually just the mass conservation which we used. So it's actually not quite an equation, it's the actual equation is just given by d by dt mvm equals to triple integral over the whole volume, and we have rho dv, right? So this is, and this of course should be equal to 0. So this is something which we got by conservation of mass. Now let's move on to our next tool, which is conservation of momentum, or momentum conservation. So here again what we do is, we know that change in momentum gives us the force. So of course by Newton's law, dp by dt is force, where p is momentum. Alright, so what we are going to do here is, let's say that the momentum actually can be given as, over the whole control volume, rho ui dv, and your ui is nothing but the velocity of that particular particle which I am using in integration, because we know that momentum is also mass times velocity. We sometimes use that term as well. So momentum is mass times velocity, and that's exactly what I'm doing here. So by Newton's laws of motion, we know that the change in momentum, so d by dt in momentum equals the body force plus the surface forces. Now the body force could be all the different kinds of force which the neighboring particles are acting. So suppose I have this particle here, I have another particle here. This particular particle could be maybe pushing this particle, or pulling this particle, and so on. So those are all the body forces which we talk about. And then we have the surface force. I'll do that in green. So then we have the surface force, and the surface force is actually due to the collisions of the particles. Actually previously I said the body force is nothing but the forces which are acting on the body, which is the gravitational forces on the body and by the body, and the surface forces will actually act due to the other particles around. Or you have a surface around here, so this surface will have probably some friction, and friction is actually known as viscosity here. And then you have different kinds of stresses, shear stress, normal stress, and so on. So those kinds of forces are known as surface forces, and therefore we need to add them as well. So change in momentum equals to body force plus the surface force. And then what how can I write this mathematically? I can write it d by dt triple integral rho ui dv equals to triple integral vmt fi dv. So this is actually the body force corresponding, plus over the surface. I'm going to integrate this only over the surfaces because these forces are acting only at the surface of the water body. So SMT tau ij nj ds. So ds, s is denoting the surface over here. So suppose you have a material volume here, so this is the surface, this is inside portion is volume, this is the material surface, the boundary of the volume you can think of. And this is a symbol which is a very famous symbol used in, be it applied mechanics or any other thing, tensorial notations actually, so that you can learn about more in detail about Einsteinian tensorial notations and other stress notations. Now to solve this equation further, what we use are again some mathematical tools, which is the divergence theorems. So divergence theorem, since I have actually denoted your everything with vectorial notation, so I'll use the divergence theorems for the tensorial notation, my bad. So I'll use the divergence theorem for tensors, and that is given as triple integral v dot del tau ij by del xj dv equals to the surface integral tau ij nj ds. So tau ij nj is nothing but the stress tensor, and then we are multiplying with the normal to get the actual force normal to the area or to the surface in this case. So what we do is we replace this quantity over here with this particular, so that we have triple integrals everywhere, and then we can group certain things and move ahead. So we have triple integral, what will this become? It will become d by dt. We had here d by dt rho ui dv equals to triple integral fi plus del tau ij del xj dv. So this is what we got as the momentum conservation equation, and that's it. So this is actually the momentum conservation equation, and through this method you can of course solve it, open it up mathematically once you have some data about the fluid particles, and then you can solve it accordingly. But whatever model you predict, it should be up to this equation, so it should solve this equation. So these were some math intensive equations which we just carried out today, so it looks a little messy over here. So we just talked about the concept of steady flow, concept of incompressible flow, and then we used the tools of physics, which is the mass conservation. So through mass conservation we derived this neat equation here, and then through momentum conservation we came across this equation. So these are the equations which whatever model we predict, it should satisfy these equations. Next, in our next lecture, we'll talk about kinetic transport theorems and the continuity theorem, which is also based on the conservation of mass theorems, and a little more other theory which we have to go. Till then, bye bye.